And so yeah, we've got just like a big amount of topics that I've jumbled into one set of slides, but they're all interesting and cool and things I need to teach you. So I'd like to start with sorting. Sorting algorithms are a topic that is nice because it helps us it's very nice, or that's what's the right word? It's logical to want to learn about sorting algorithms in a CSCI 41 class because we understand the concept of sorting. Like we want to make a bunch of numbers that are jumbled become increasing or decreasing. And then we want to analyze all the different kinds of sorting algorithms because they all have different running time complexities and also space complexities. So that's exciting. And let us learn about those things. So I did talk about sorting algorithms when I taught my CSCI 40 class, but you maybe have not heard too much about them in your version of it. That's okay. I will start from scratch here, but if you took my CSCI 40 class, you may see a lot of familiar things, but we'll hit them in more detail this time. So if you would ever like to try out, and I highly encourage it, your sorting algorithms that you're going to eventually be forced to read about, if you have not already, there's a nice handy way to make a bunch of numbers all jumbled very quickly. Here is the C++ way of doing it. There's a random header, there's an algorithm header, which we know about, and then this chain of weird sequences of lines is going to shuffle your vector. If you have a vector and you want to jumble it so that you can try your sorting algorithm again and time it a bunch of times, this randomly shuffles and jumbles a vector called v. So you need to make what's called a random device, the weird object that is a source of randomness, and then this is a specific kind, a standard kind of random algorithm that produces random numbers, a generator called G, based on this random device. Don't worry too much about this, I barely understand it. And then the shuffle function in the, I believe it's the algorithm library. You give it the extent of the vector you'd like to shuffle and jumble around, and you give the random number generator right there, the one that you want to use. So that's these three lines, after including these two headers, will shuffle and jumble a vector that you want to test a sorting algorithm on. So that would work. It's you can push back a bunch of numbers from 1 to 100 or 1 to 1,000,000, then shuffle them all, and then run your sorting algorithm. And you can do that a bunch of times and take the average amount of time it took. So yeah, that's one way to do it. But I just want to kind of jump in and talk about a bunch of sorting algorithms. So let's see here. I would like to give you this link eventually, but let's start for now. There's a bunch of different cool animations for sorting algorithms, and here is a lovely website that is one of them. Your book, of course, also has beautiful pictures, but I like this website. It's fun. And I'm going to use that to visualize the sorting algorithms. It's going to be very cool and pretty. So the first sorting algorithm I'd like to teach you is probably the simplest one to understand that it's going to get the right thing in the array or the vector. But let's see also that it's a little inefficient. So the job of bubble sort, the job of any sorting algorithm that I want to talk about today, is you take a bunch of jumbled numbers. Let's say we got a number, an array or a vector of just integers, and we'd like to sort them in increasing order. So let's see, let's say I have 5 elements. 1, 2, 3, 4, 5. And honestly, the worst case for bubble sort is when they're perfectly in reverse order. So let's deal with that. What bubble sort does, this is pseudocode for bubble sort. What it does is it's going to do this inner code a bunch of times if something's true, and this inner code is something that should be familiar to you. It is a swapping algorithm. See how that's going to swap some stuff? It's going to swap elements at index j and elements at index j plus 1. It's going to swap two things that are right next to each other in this array called numbers, or vector called numbers. All right, so that's what it takes. It takes a vector or an array called numbers, and also its size. If it's an array, you need to pass that, right? And then it's a doubly nested loop, and essentially what it does is if it sees that the numbers that are right next to each other, j and j plus 1, j is going to range through all the valid indices. If it sees that two numbers in this array or vector that are right next to each other are out of place, like the one that comes before is bigger than the one that comes after it, they're out of sorted order at that point, then it swaps them. All right, so that's all it does. That's all bubble sort does. It sorts an array by swapping elements that are right next to each other. And so it's going to, like, at the start of time, it's going to consider these two elements, 5 and 4. Are they out of order? Yes, right? Because index 0 is bigger than index 1. That's the wrong way, right? So we need to swap them. And then that will make this array slightly closer to being sorted. You see that? So it looks at these guys and like, oh, they're out of order. Let me swap them. So it's going to swap. I guess I'll keep that. They're out of order. It will swap the 5 and the 4, and now it's 4 and 5. Yeah? So that's after one round. And then it's going to try. It's going to advance j. Don't worry too much about this outer loop. Then it's going to advance j again and be like, all right, indices 1 and 2. How do they compare? 5 versus 3. Are they out of order? Yes. And so it's going to swap those. It's always going to like zoom in. It's very, what's the word, myopic, I guess. It's going to zoom into the array and only look at things that are right next to each other. It's going to like block the vision everywhere else. So 5 and 3, are they out of order? Yes. And so it will swap them. And now it's 3 and 5 right there. So do you see how the array is still not perfectly sorted, but it's getting closer to being sorted? Does that make sense? What's happening here? So yeah, we're just like working on this inner loop once. Don't worry about the outer one just yet. And then it advances j++. It's like, all right, index 2 versus 3, 5 and 2 are here. Are they out of order? Sorted wise? Yes, of course they are. So we will swap them. So it does the little swapping algorithm. And now we got 5 and 2. Become 2 and 5. And now the very last round of this inner loop, the first time it happens at least. Dun, dun, dun. We got 5 versus 1, out of order again. Let's move them. So 1 and the 5. So 1 gets swapped with the 5. And now the array is kind of hard to read, but it's 4, 3, 2, 1, 5. So initially it was 5, 4, 3, 2, 1. But after one round of this inner loop, do we all see that 5 is in the right spot? We never have to touch that last index ever again. The biggest thing moved to the very end just by the nature of that if statement and the swapping. So that after one round of going through the array, we know that that last index is taken care of. We never have to look at it again. And so that's nice, but we can play that same game then with this smaller array. You see it? And so that's what this I variable is doing. It's like, all right, I kind of is taking into account the number of times I'm, in the worst case, going to have to go through this array. And if you think about it, it's like, all right, another round is going to get the biggest thing right there, the next biggest thing right there. And then we'll have to go through the size 3 array, and then the size 2 array, the size 1 array. We have to go size -1 times to play this game. And that's exactly what this outer loop is doing. Does that make sense? That's kind of how that works. So the I variable is keeping track for the worst case number of times I got to go through this array and swap things that are right next to each other. And it's always the next biggest element will win out and be placed. Like it's always like we're considering a subarray sometimes, the next smaller array. And like once we go through all those pieces, swapping things that are right next to each other, the next biggest element's going to end up on the right side. We never have to touch it again. So it's not going from j to size -1. It's going to from j equals 0 to numbers size -I -1 because it's moving inwards each time. It has one less element to look at in the subarray that still needs to be sorted. All right? Do those words make enough sense? It's just pseudocode. It's a little weird, but that's what bubble sort does. It's going to swap things that are right next to each other. It's not really looking at the big picture. It's just like it's really zooming in as far as it possibly could. And well, in the worst case, you got to go through this array, size -1 times, playing this game on a smaller and smaller array each time. So the rightmost index gets smaller and smaller. So that's not horrible, but it's still not great. And so on this page is a wonderful, just what's the word? A pictorial version of bubble sort in action. If I click randomize array, this is like an example array. There are numbers in this array, and then also the bars kind of indicate how big that number is relative to all the other numbers in this array. So 84 is this, and 55 is this. So it's going to run bubble sort. It's going to highlight the things that are right next to each other. You're going to watch them swap. And then also by the end, you're going to see that a sorted pictorial version of an array with these bars is going to be perfectly increasing in perfectly increasing order. All right, so that's what's about to happen. So I'm going to click randomize again, why not? And then I'm going to click bubble sort, and you're going to watch it go through and like highlight the things it's looking at and then swap them. Swap the ones that are too small. Look at him go. Swap, 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 swap. It's very slow. I can make it faster with the speed. Boop. There they go. But the very first round, you see the biggest thing, it's always moving to the right. You watch it, we're doing that? Wherever the biggest thing is, it's always going to make it to the end. And then that next biggest element is in the right spot. We never have to touch it ever again. We don't have to look at these big things on the right ever again. They are in the correct position. We'll just sort the rest. We'll bubble sort the rest of that smaller array with one fewer index. So yeah, that's how it works. And so it's going through a smaller and smaller array each time. On average, the smaller array is size n/2, I guess. And then it's considering elements that are only right next to each other, swapping them if they're in the wrong spot. And so in the worst case, like if you had let's say that this was the smallest element, every round it just moves one to the left. Yeah. Right? So if it was at the very end, you need all the rounds to get it to where it needs to be. And so, yeah, there it is. It's sorted now. And does that animation help understand kind of the idea of bubble sort? Any questions about that? So going back to the code, I hope that's more clear now. But the analysis is it's n squared for sure. This inner loop is constant time, right? Or sorry, this inner body of the inner loop. Constant time to do a swap and some condition checking. This outer loop is for sure going to be, it's going n-1 times, so it's doing O of n executions, right? O of n runs of its body. And then this inner loop is the only thing that's a little weird. How many times does it run? It depends on what I is. So if you think about it, at the very start of time, on average, I guess, the size of that inner loop, or the number of times it's going to run is like, average is like n/2 times. Because sometimes it's like it gets down to an inner loop where the subarray is only size 1 or something, and then at the very start it's size n. It's decreasing by 1 every time. Something like that is what's going on. And so at the start of time, like you're going through, you're looking at n indices. You can imagine that. Or it's really, this is ranging up to, because it's always j and j plus 1. So it's going up to index n-1, essentially, and then adding 1 to it. So n-1 rounds of the swapping and the checking the very first time, and then it's n-2 the next time, and then n-3 the next time. So that's what it's doing. That's how many rounds of this inner bit of the loop is happening. Does that kind of make sense? The very first time we got to go through n-1 elements, then it's n-2 elements, then it's n-3, doing constant work at each element, all the way down to where I is size -1. So let's see. Number size minus 1, plus 1 minus 1. It goes all the way down to like something like 1 or 0. So there. And so the idea is we have to add up these all together, and there is a formula that ends up making it like n squared plus some other stuff. So that's why it becomes O of n squared, if that makes sense. So everybody know that there is a formula that adds up like n, what is it? 1 plus 2 plus 3 all the way to n is equal to, first, like the trick is to do it twice. You add this to itself, right? And then it's, you get n plus 1, n times, but you counted it twice, double, so it's over 2. And so that's why you see the n squared. Does that kind of make sense? Have we seen that formula before? Like that's a thing. That's a thing, and that's why it's n squared. So, because this is really decreasing, but not enough to get rid of an extra n. All right, so that's my hand-wavy analysis. You'll read more about it in the book. I just kind of want you to understand the intuition behind the sorting algorithms, because like you're never going to want to program bubble sort. It's the worst one. Okay, but yeah, I think that's what I wanted to say. Are there any questions about that before I show you others? Okay, so what I do want is for you guys to try this page. Like click randomize array, click these other ones because there are other sorting algorithms. And I'd like you guys to get together in your peer instruction groups and try to write down the order of like slowest to fastest. What is the slowest one of these algorithms? Hint, it's bubble sort. And what is the fastest of these algorithms? And try to find your order. You can watch them work, just get some intuition. I think that would help. And here, I'll give you this link. What's the best place to give it to, honestly? Maybe Discord? But then not a lot of us are on Discord. Here, what I'll do, watch. I will clear out the written ice page. You can also, you're going to make your own post, but here, I'll give you the link in a post. Ta-da! So you can go there, and then you'll make your own with your thoughts. All right. So yeah, please go to this page, click all the buttons. Please click. Remember to jumble the array between the clicking of the buttons, but try to come up with a good order for like what's the slowest one of these sorting algorithms and what's the longest sorting algorithm. What's the fastest? Sorry, sorting algorithm. And then we'll talk about them in detail, except for one of them.
Oh, for those of us to this class, I just did party on the third of the slopes. We'll get extra credit, we'll show you that we'll get.
Yeah. You just gotta show me that you're there. Show me in the Discord message. Because I was on the survey.
Well, just post it on your
Send me a private message.
What?
Send me a direct private message.
All right.
Nobody else needs to see your selfie. Please and thank you. What are the options? There's one called quick sort. Is that really the fastest? Find out. One was really weird. Interesting. Got a couple minutes to play around. All right, another minute or so, then we'll come back. I guess you could set a stopwatch and try it. But you might just get lucky on one of the runs, who knows? Interesting. All right, that's my timer. Let's see. Let's see what we're thinking. Let's see if we found a good one. a good order. If we all agree, even. Definitely bubble sort is the slowest. Interesting. Look at us. We agree that it goes bubble sort, selection sort, at least so far. Does everybody else agree with that? Remember to press submit. We think that shell sort is decently fast. Shell sort is not one that I'll teach you, but we can look at it together if you remind me. It's a weird one. All right, I'll just assume we think these other things. We're a little shy today, maybe. That's all right. Well, yeah, it was worth exploring because that gives you more intuition. So here, let's go and talk about some of these other ones. Let's start with selection sort. There's an order that I've picked here. Yeah. Selection sort's job is it's got a bunch of numbers. Of course, it's going to sort them again. Numbers and their size. And it's again a doubly nested for loop, so it's again going to be n squared. It'll do constant work in the main body of the innermost for loop. But it's still going to be faster than bubble sort. It's still going to be faster because like the constant out in front in the n squared is not as bad. It's not going to go zooming in and just looking at things that are right next to each other. It'll try and look at the big picture, and that's better, even though it's still n squared. So here, what selection sort is all about is it's going to go find the minimum in the rest of the array that needs to be considered and put that minimum in the correct position, all right? So bless you, let me try and walk you through that. So here it is, it's going through all the indices because you got to fill in every index, right? I is going to take on the index we're trying to fill right now with the correct value. That's the goal of the outer loop. It's like, all right, this is the index that I would like to fill with the correct value in sorted order. So at the start of time, we don't, like it's index 0 we'd like to fill in, all right? That's what it does. And so what it does is it looks through the whole darn array and it finds the value that should go there is the minimum value, right? It's going to go and place the minimum value right there. So that's what it's going to do. The index at the smallest, like at the start, it's the guess. It could be index 0, I don't know. And then it's going to go through everybody else, I onwards, till the end of the array. And if it finds something smaller, that's where the smallest thing is. And then at that point, it's like got an index that it's trying to fill and an index of the smallest element. It's always going to have the minimum. And then it's going to swap the two. It's going to make sure that the smallest thing is at the index that it's trying to fill. So like at the start of time, it's index, like let's say it's 1 is the smallest thing. We've gone through everybody and made sure that 1 is the smallest thing. We've placed it right there. Does that kind of make sense what's happening there? Selection sort, selecting the minimum, we say. All right. And so it's better than bubble sort because it has the big picture in mind. It doesn't just look at things that are right next to each other. That would be inefficient. So it's a little bit better, but it's still going to end up being n squared. Because like the next round of the loop, we never have to touch this index again, right? Again, the array gets smaller. So we're going to go through all these elements from index 1 onward. So that's why you see this j value starting at I plus 1, right? Just everything afterwards. So we're trying to fill in this index now. We'll go through that and everything else and find the smallest thing and we'll shove it right there. Index, maybe the number is 2. I don't know. But then, yeah, at that point in time, like you have a side of the array that's already been sorted. We don't have to touch that side anymore. Those are the smallest things. That's in the right spot already. The rest of the array is unsorted. And the next round, we're trying to fill this element, right? That's how it's going to work. So it's going to go through everybody, look at the entire rest of the array, including that element, and swap the smallest thing to be right there. Okay, so again, the array gets smaller and smaller and smaller, the one that you look through, but it's still going to be n squared, all right? A bit faster than bubble sort because it's not swapping too many things all at once. It's only swapping things that are important to need to move right now, all right? That's how that works. So let's try to analyze this and understand why it's n squared. It's going to have the same game as bubble sort, and I'll try to make it more clear. So here, dun, dun, dun. Yeah, so this outer loop, how many times is it going to iterate? N minus 1 times, so that's O of n times, right? This inner loop, how many times is it going to iterate? We'll have to count it for real, but it starts, like originally it's going to start from 1 to n minus 1, then it's going to be 2 to n minus 1, 3 to n minus 1, because it depends on I. On average, it's going to be O of n times. You can think of it that way. I'll prove to you why. And then the inner bit here, this is constant. Constant work. N times constant, essentially. All right, but I'll prove to you why this is hand wavy right here. I'll fix that. But after that, this is part of the outer loop right now. To actually do the swap once you know where the minimum is right now, That's, again, constant time. All right. And so the reason you can say O of n here, and the reason it becomes n squared, is because if you think about it, let's consider just this entire body of the outer loop. What is it doing every round? How much work is it doing every round? So it's going to go and it's going to look through at the start of time, right? You've got every element. We got to look through. We got to look through everybody and find the smallest and put it right there. Yeah. So that involves going through the entire array. Yes. You're visiting all n elements, doing constant work at each of them, trying to find the minimum. All right. So n amount of work done the first round, plus, and then I advances. Now it's size. Now you have a n minus 1 sized array to go look through, find the minimum, place it at the next index. Yeah. So you're going to do constant work at each remaining element. So now it's n minus 1 work to do that round. And I think you see like, okay, now I have a size n minus 2 array like this one right here. Size n minus 2 array to go through, constant work at each element, go and find the minimum, swap it back. Swap it at that index now. So n minus 2 work all the way down to until we get to a size, like we get to right here, right? We got to find the minimum in a size 1 array. It's already there. We found it. So it's just constant work to swap it with itself or just notice that we're done. And so it's all the way down to 1. So that's essentially the analysis. It's that many steps of work, kind of. How many elements we're looking through. Just multiply all that by constant time at each element that we're looking at. And there is a formula for this. If you've never seen it before, I might as well teach it to you here. If some of us haven't. It's a nice little trick. Here's the way I learned it. If you want to add up the numbers 1 plus 2 plus 3 all the way to ... n minus 1 all the way up to n, the way you can think of it is like just do it twice because that makes it easier. So like this is what we really want to know, this summation, this addition problem. We want all those. Let's just add it to itself, because if we add it to itself, we'd have 2 times the right answer. We'll just divide by 2 at the end. So here, the way we add it to itself is the cool way. Watch what happens. We'll add it to itself, but reversed. So let's put the n here. Let's put the n minus 1 next to the 2. Let's put the n minus 2 next to the 3. Plus ... all the way down to like this is 2 and this is 1. So that's the same thing, just reversed, right? And now you can line these guys up. This is the trick that gives the formula. You can line those up. You can line those up. What's true about all of these? They all add up to n plus 1. You see that? So it's n plus 1. How many times? It was n times, right? N plus 1 at each of these, n times. But when we do it this way, we double count it, so we just divide by 2. And so that's the analysis. And so if you factor these all out, do you see how that becomes O of n squared, whatever that answer is? Because you got n times n eventually. So you're going to distribute, right? So that's why that is like that. And so now we know this turns into n times n plus 1 over 2, which is O of n squared. Theta of n squared. And we still need to watch it work. I guess you clicked it already, but I'll show it to you too. But does the analysis make enough sense? Any questions about that? Can you read the pseudocode and implement it yourself? That's all I really care about. And it's mostly just like, if it was a vector, you just do dot at, but honestly, you can just copy and paste most of this. So yeah, it's still n squared, but it's a better n squared than bubble sort. It's fewer things to go looking at, all right? So here, let's do selection sort, and you're going to watch it highlight the minimum. That's like its best guess of the minimum. There's its best guess of the minimum. It's going to update its guess every time, like, and then it's going to place that minimum at the next index that needs to be filled. And then this side of the array is perfectly sorted. We are good to go. Yeah. And I hope it makes more sense now. So that's what it's doing. It's thinking about the big picture. What is the next? I've got a next element to fill. What should go there? The minimum and the rest of the unsorted stuff. Beautiful. And it's still n squared, but it's got less swaps to do. It's looking more at the big picture, so it's a better n squared than bubble sort. Okay? So that's the algorithm, and that's probably the next one in fast order. Cool. Any questions about selection sort? So selecting out the minimum. Kind of logical. I'm sure that you've sorted papers or cards in your If you like got dealt some cards and you're playing a card game, like maybe you're going to use selection sort to go put them in order in your hand. And that's a common one that humans use. So yeah, that's selection sort. The next one is insertion sort, still n squared, but it has a better best case. I'll show that to you. Insertion sort is also much better than bubble sort. Insertion sort is probably one of the better ones. Shell sort is an improvement on insertion sort. I'll try to show that to you. But what insertion sort does is it's hard to think of another way to sort things that wasn't selection sort. Like selection sort seems right. Like just put the next thing in the place it should go, find the minimum. Insertion sort is going to try to do something different. It's going to keep the first few elements sorted, and it's going to bring in a new element each time and put that in sorted order. So it's going to keep track of a locally sorted subarray, and it's only going to sort up to an index that it's looked at so far. So yeah, kind of here's the key bit that's hard to explain. It's like if insertion sort has sorted up to index 5, it's never looked at anything else from index 6 onwards. That's the difference between it and selection sort. It's going to be the first 5 elements in the original array are now in sorted order. It has not considered anything over here yet. That's the goal. It's not moving things outside of that range of indices. It's always bringing in the new thing down to where it needs to go. A drawing is worth 1,000 words. So here, let's talk about it. So here's the code. It's still a nested loop, but it's a for loop and a while loop now. Ooh, different. Let me try to draw what insertion sort does, because it's really cool. It's a different idea. So it's harder to implement, but it's probably the best n squared sorting algorithm that is not shell sort. Shell sort is an improvement on it. How many elements do I want to deal with? Well, let's pretend we have 8. I think. Yeah, that's my example. So let's say we've got 8 and 2 and 5 and 4, 3, 9, 12, and 15. All right. So what insertion sort's going to do is it's going to have like at the start of time, it's going to be like, I'm going to make a small array that I know is sorted and keep it sorted even as I expand how big that smaller array is. I'm going to keep track of a smaller array that is sorted and bring in a new element each time. So at the start of time, it's going to like draw lines like, all right, everything to the left is sorted. It's a small array, just 8 by itself. That is a sorted array, right? That's fine. So that's what it's going to do. And then it's going to expand its frontier. It's going to discover new land, and it's going to bring in the 2. It's like, all right, the 2 is a new thing. I'm going to consider both of these. 8 was the sorted array. I brought in the 2. Where should it go now relative to what else I have here? And so what it's going to do is it's going to move the 2 downwards and move the 8 up. So 2 is going to be brought down to where it needs to go, and everything else is going to shift away into that. Okay, so that's how insertion sort works. So it's going to bring in the 2 now it's going to sort. It's like, okay, 2 and 8. And so it's sorted up to index 1, which means the first 2 values of the original array are now in sorted order. Does that make sense? Like, we know that the 3 and 4 belong between, and the 5, belong between the 2 and the 8, but this algorithm has not yet looked at those yet. It's not considered them yet. It's always going to bring in the next thing from the array and not look at anything past it. It's going to bring the new things down to where they need to go. That's insertion sort. So let's try to watch that work. So it's going to do it a certain number of times, and it looks like, J is the new index. J is the new index that I'm looking at. So now let's say it's index 2. That's the new thing. I've expanded my frontier, broadening my horizons. I brought in the 5 at index 2, and now we need to swap it down. We need to shift things away and swap it down to where it belongs, because it needs to go between, right, the 2 and the 8. So that's what's going to happen. It's going to do that. It's going to swap it down. So while I haven't gone past the end of the array, and the thing that I see before is bigger than the thing I'm at right now, that means they're in the wrong order. It's kind of like a bubble sort, essentially, in reverse order for that new thing. It's just going to swap them down, shift everything out of the way, move the 8 up and the 5 down. Yeah, get them down to where they need to go. It's going to work in that direction. So it's going to swap the 5 and the 8. And so now it goes 2, 5, 8. Do you see that? 2, 5, 8. Don't have enough room to put it all there. So it goes 2, 5, 8, and none of these guys have been looked at yet. Does that make sense? That's the difference between insertion sort and selection sort. Selection sort is like doing it all at once. The real thing that needs to go in index 0, put it there. insertion sort is like, I bring in a new element, bring it down to where it needs to go. I'm going to keep track of a locally sorted subarray of the original indices and those, of the original elements in those indices. So yeah, that's how that works. And so for the next round, for example, it's going to expand its frontier, bring in the 4 to where it needs to go. So it's going to swap it down past there, right? It's going to go down and go before the 5. That's where it's going to end up. Okay, and so that's what the while loop is doing. It's just like moving it down, swapping them down until it's in the right spot. It's like a reverse bubble sort. But it's doing it as efficiently as possible. So yeah, any questions about the intuition behind it? Does the drawing make enough sense? Because the code is doing that, essentially. And the analysis is, hopefully by now you agree with me, even though it's making the things smaller and smaller. Like it's, I guess now it's going in reverse order. It's making a bigger and bigger array that's sorted. So that's what it's thinking about. So this is going n times. I don't know why I'm in green still. Let me go back to blue. So this is happening n times, O of n times. And then this while loop, the first time it doesn't have to go down as far, but once you get to the last index, it may need to go all down to the very start or something if it was the smallest element. So on average, it's going to be O of n. And so for the same like formula game you could play with this, for the same reason, it's essentially n here. And it's doing constant work at the inner body, so it's n squared. All right, that's the worst case. So yeah. However, though, in contrast to selection sort and bubble sort, there's also a best case that is not n squared. Surprisingly, selection sort is always going to go and find the minimum and put it where it needs to go. It's never going to look and see like, hey, do I not have to do any work right now? Insertion sort's nice because let's imagine this was like a 9 here. It doesn't have to move right now, does it? Like, I expand this. Oh, the 9's already in the right spot. It doesn't have to do anything. It doesn't have to bring it down at all. So if the array's already sorted, like you're going to have that game in every index, and it just like looks to the left. It's like, okay, it's already fine. I won't move it. So it's best case is just like, look at everybody. It's linear. So that's what happens if the array is already sorted, or it's very close to being sorted in that you only have to move indices a constant number of times each round. So that's kind of cool to think about. That's insertion sort. So here, let me click it, and then we'll see if there's questions. So you can watch this little frontier. It's going to be like increasing, but there's still going to be bad like elements over here that eventually need to move down. So you watch it, bring in a new thing, and swap it down to where it needs to go. If it was, sometimes it doesn't have to swap very far, but other times it does. Like this 1, for example, that belongs at the start, and that's going to involve some work, but this 88 right here won't have to move down too far. Like go to here. See, it was immediately done. So it depends on the shape of the array. That's different now. That's different to bubble sort and selection sort, where you just gotta like do it all, always, n squared work, no matter what. Insertion sort, you don't have to swap it down too far if it's not that out of order. That 11's gonna go down very far, but they're not all like that. Okay, so because of that, insertion sort is probably the best n squared algorithm, and I hope you can agree with me. Because of that, it doesn't have to swap things down as far, depending on the way the array is arranged. So that's kind of cool to think about. And if I click it again right now on a sorted array, it'll just like, boop, I'm done. It's just going to make sure that everybody, like it's going to bring in the new thing. Do I need to move it down? No, I don't. It's done. So it's O of n if it's already sorted. That's kind of cool. I think that's all that I wanted to say about insertion sort. Are there any questions about it? It's like bringing in the new thing down to where it needs to go. Bringing the new thing down to where it needs to go. If it doesn't have to move very far, that means it was already mostly in the right spot. So that's great. A lot of us saw, or we thought, that shell sort was really fast, even faster than quick sort in some cases. I'm going to click shell sort and try to show you it. What shell sort does is it's doing like a bunch of insertion sorts, in a sense. It's moving things closer together and then doing insertion sort, because you know that things that are close by get sorted very quickly by insertion sort. So it's making things closer and closer together each round. Oops. Refresh. Shell sort. So I encourage you to go to the Wikipedia. I don't think it's in your book or anything, but go look into shell sort if you'd like. It's like doing a smaller array each time and insertion sorting those And so then it's got a bunch of chunks of arrays that are all close to each other. That's essentially what's happening. So it's kind of cool to think about, but it's like an improvement on insertion sort. The worst case time is still n squared for shelf sort, actually. So, but it's better. It's better, especially for a small amount of numbers. You see the n squared if the size was like bigger. Like this is a giant thing. Watch shelf sort work. It's gonna take a while. So cool. But yeah, those are all of the ones that are n squared. You got your bubble sort, your shell sort, your selection sort, and insertion sort. Okay? I would say that's the order of speed. Bubble sort, then selection sort, then insertion sort on just an arbitrary array. For reasons that I hope I have explained well enough. Are we ready for the ones that are better than n squared? This is exciting. So to get to those, sadly, we need recursion. Recursion to the rescue. So it's both of the ones that I want to teach you at least are called divide and conquer algorithms. And a divide and conquer algorithm is, it has to be recursive. That's what one of the requirements. It's recursive, and then also it's conquering. It's recursive in that like you're splitting things, and then also you're splitting things evenly and conquering them. They don't overlap at all. And I'll show you what I mean by that. So like what will happen in a divide and conquer algorithm? It doesn't have to be a sorting algorithm. Like it's just, that's an adjective that describes certain classes of algorithms. They're not just sorting algorithms or divide and conquer, but they're a good example of them. What happens in a divide and conquer algorithm is you've got your problem. Again, you're breaking it down into smaller problems with recursion, assuming that it all works out, and you get to your base case. That's fine. That's just recursion in general. And then you build up your answer using the results of the smaller problems, and there was no overlap between them. So what I mean by no overlap is, like, say you want to sort an array. What a divide and conquer algorithm would do is it would chop it in half and sort the left half and the right half separately. What a non-divide and conquer algorithm that was recursive would look like would be something like this. It would take, there would be overlap. It would need like to do something with this piece and maybe also something with this piece. You see how there's overlap of elements there? That's not divide and conquer anymore. But a divide and conquer algorithm is like chop it in half or thirds or quarters or whatever, and then just like individually deal with those halves or quarters and bring them back together in some normal way. So this is going to be a drawing I'm going to do again because this is merge sort in general. But here's a good example of a sorting algorithm. All right, let's cut the array perfectly in half, and then let's go and recursively sort this half and sort this half. Yeah, that's not horrible. And then you know that the recursion will get down to base cases. This is like still an array that has a lot of things in it. Like the recursion will then like chop that in half and make this size array. Sort that one recursively. Sort that one recursively. And the idea, like that'll happen again and down until you get to the base cases. So let's say maybe your base case is size 2. Like these are all now size 2 or something. You just like look at each element and swap them if they're out of order. And so essentially, now I've got this is sorted, this is sorted. There's a way to look at both of these at once and bring them back and then make that original slightly bigger array sorted. Does that kind of make sense? That's what's going to happen. Just I'll pretend that the recursion sorts these guys, bring them back up. Now these smaller pieces are sorted. So when you're actually composing the algorithms, like, all right, I chopped it in half, I called the recursion, assume I've got 2 halves of an array that are now sorted for me. Just like go through them and bring them back together into the original array, and like it's easier once the 2 sides are sorted. It's like what's the question of what goes here? It's just like look at this thing and this thing, right? Those are your 2 options of the first element in the sorted final thing. So those are the 2 smallest things of those. It's forced to be one of them. So yeah, you build up the solution using the results of your non-overlapping subproblems, and what I've just described is essentially merge sort. So I will draw that picture again. Look forward to it. But that's divide and conquer in general. It doesn't have to be sorting algorithms that are like this, but the 2 sorting algorithms that I want to talk to are divide and conquer. Right? Let's talk about quicksort first, because it is honestly supposed to be the fastest. On general arrays, it is the fastest sorting algorithm. There are slight improvements. Like Python uses a weird version of quicksort. It's called timsort, I think, named after a dude. But quicksort is like the granddaddy of it all. So what quicksort does is it sorts an array in place. So By the way, we should probably be talking about space complexity, because quicksort versus merge sort. That's kind of the trade-off. If we just look at all these, constant space complexity for bubble sort. Can we read that off the algorithm? Do we see that? Like you were given the array, you can't not have the array, but like I and j and temp, right? Constant amounts of memory. Constant space for bubble sort, constant space for selection sort, I, j, index smallest, temp. Those are all the things you need, right? Constant amount of elements, no matter how the size of the array. Insertion sort, constant space, I, j, and temp again. Yeah. Quicksort is also going to be constant space, but the time is going to be better. We're going to turn an n into a log of n, so it's going to be n times log of n, log base 2 of n. Okay, so let me try to explain quicksort. I'm not going to give you code. Your book has code. It's a little complicated. It's recursive, right? So let me try and talk you through it though, so that you can understand the code when you get to it. So quicksort is the main recursive algorithm. And then it calls off to a helper function called partition that moves the array around. It jumbles it in a nice way that quicksort can understand. Okay, so what quicksort does is it initially calls partition on the subarray that it's trying to quicksort right now. Originally, it's the whole thing, right? You're going to give the whole array to quicksort, and the very first thing it's going to do is give that entire array then to this partition function. Okay, let me try to explain what partition does. It's going to move things around, something called a pivot element. So let's say we have a size 5 array, just to make it easy on ourselves. Let's say it was 5, 8. Wait a second, no. Yeah, 5, 8, 3, 2, 6. That's a good one for an example. All right. So the very first thing partition does, it takes a piece of the array. Usually it's for the best running time, it's supposed to be a random element. Let's pretend that partition always just chooses the first element of the subarray called, and it's going to call it the pivot element. All right, it's going to pivot the array around it. So it's chosen 5. All right, so 5 is our pivot element, and it's going to make sure now, it's going to go through the rest of the array, all these guys, and it's going to pivot everybody around the 5. It's going to make sure that everybody smaller than the 5, smaller than the pivot element, is going to be on the left side of this array, and everything bigger than the 5 is on the right side of the array. And it can do that pretty efficiently by taking two like pointers or indices. It's like, here's the left side, here's the right side. Are these in the right spot? Like, who's in the right spot right now? The 8 is in the wrong spot. It needs to move to the right, right? 6 is in the correct spot. It's supposed to be on the right side because it's bigger than 5, right? 8's out of order, 6 is, 8's out of order, 6 is in the right spot. So we'll move in to now consider the 8 versus the 2. It's like it's bringing two indices inwards. So now it's 8 versus 2. 8's out of order, 2 is also out of order. Once it has both of them, it'll swap them. So now it's got, we'll put the 2 here and the 8 here, and then it'll move this left index up and the right index down. Now it's 3 versus 3. When they meet, we're done. All right. Do you see how that essentially very efficiently has put, it's kind of chopped this array in two, right? It's got things smaller than 5 right here and things bigger than 5 right here. Does that make sense? That is closer to being sorted, yes? That's better. And then also, where they met, where these two indices met, that's actually the spot where the pivot belongs in the final sorted array. Can we see that? The 5 belongs at that index. So that's why partition is doing a really cool thing here. It's going to end up being very fast for us. So that was, it's essentially a linear time process. Partition is linear time. To go through the array, swap things around, and get smaller things in the pivot on the left side, bigger things in the pivot on the right side. And then it also is going to get the pivot in the right spot. So it'll swap the 5 and the 3. So now it's got the 3 and the 2 right here. And it's got the 8 and the 6 right here. And the 5 is done. It does not need to be considered ever again, yeah. And so not only do I have two smaller arrays to quicksort, but also it's not just the size of those arrays does not add up to n anymore. It's now n minus 1 because I've got the pivot in the right spot. I never have to touch that again. So it's very efficient because of this. All right. And so now you're going to call off to recursion. All right, here's a small array, go recursively quicksort that. And here's a small array, go recursively quicksort that. And once it's done, it'll be in the right order. All right, does that intuition kind of make sense? That's what partition does. And then you just recursively, it's a smaller thing now, go and quicksort it. Just imagine it'll work out. Okay? So yeah, that's what quicksort does. It partitions whatever its current size array is with respect to a pivot element that it chooses. It's supposed to be a random element, and that's the best way to pick a pivot element, because you could choose a bad one that like doesn't cut it in half as well as it should. Then you put that one element in the right spot, because the pivot's going to end up in the right spot at the end of the partition. And then you got two smaller, unsorted still subarrays to call quicksort recursively on. They're smaller, so you just let the recursion handle the rest. We trust in the recursion. Okay, that's quicksort in a nutshell. So you're going to look at the code. You're going to look at animations in your book. That's what I want in the back of your mind. All right, and so I'm going to prove to you that it's n log n, but that's what's going to happen. All right, there's also a cool YouTube video that I want to show to you. It'll be funny. Some people made a dance to quicksort. I want to show it to you. It'll be cool. But essentially, the name of the game is you can turn one of the n's, because like all the other algorithms were n squared, you can turn one of the n's into log base 2 of n because you're cutting things in half. That halving like should remind you of binary search, right? And you can only do that so many times and still have things. So that's the goal. So let me try to explain that first, and then I'll show you the animation and then the dance. So, okay. This is average case complexity. So on average, quicksort is n times log base 2 of n, or n log n we say. That's how much time it is, and it's logarithmic space as well. Let's see. Dun, dun, dun. I think, yeah, that's what I want to say. So it's logarithmic space because it's got to call itself recursively, and you know that the stack, right? The stack will be, in the worst case, once you get down to the base case, log of n high. Log base 2 of n calls. Big O of log base 2 of n calls. Let's put a tilde right there. Recursive calls. So that's I'll show that to you in a second, but that's what's going to happen for the space complexity, but we want to deal with the time complexity right now. Let's put that right there. All right, so that's the average case, if that works out. It'll look like that. There's also a bad case. There's a worst case that's worse, but usually you don't get to it if you choose a random pivot element. You'll never have that happen. But okay, in the average case, here's what's going to happen. All right, you're going to probably choose an element as your pivot. If you choose it randomly, at least, that's going to be kind of in the middle of the elements, right? If you choose a pivot element that's kind of in the middle of the elements, it will end up here-ish, right? And you'll end up with an n over 2 sized array over here and an n over 2 sized array over here, yes? To make this happen, the partitioning process had to like start here and over here, like work its way inwards. It was had to do some swappings. It had to visit n elements, right? N elements visited. Something like that. And you're doing constant work at each element, essentially. So that's what happens. And then you hand off to recursion this smaller array that's been essentially cut in half from this smaller array. Yeah? And then you do the process all over again. It's like, all right, when you call it recursively on this jumble, it's still jumbled over here, right? When you call it recursively on this jumbled array, it's going to pick a pivot element. If you do it on average, right, it's going to choose one that's kind of in the middle of these numbers. And so the pivoting process, the partitioning process, is going to put that element here, and you're going to end up with essentially this many array, right? Elements on each side, they're about cut in half again. So that's what happens. That's going to happen over here too, on average. You're going to choose a pivot element that's going to be about in the middle of those things, maybe a little bit on the left, a little bit on the right, but you're going to end up creating essentially another half-size, two more half-sized subarrays to go and quicksort. Okay, so that's the goal in the best case, or in the average case and the best case. That's what happens. All right, and then how much work are you doing to partition this array, this smaller array? You got to look at n over 2 elements, right? N over 2. I'll just say swaps. Dun, 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 but really it's half of that. So like n swaps, n over 2 swaps over there to get things in the right spot. But that's kind of what's happening, n over 2 swaps. So it's at each level, it's n work, right? N work on that level because n plus 2, n over 2 plus n over 2. And then again, it's going to recursively bring down these guys. Recursively quicksort and partition and quicksort those. Cut them in half as many times as we can. So this is like n over 4 swaps or something to do the partitioning process and get things in the right place. Yeah. And so the question is, well, you get down to the base case when you have like a size 1 array. Does that make sense? If your array is size 1, it's already sorted. That's a good base case. Or size 0. Like that can be your base case. The question is, how many recursive calls do you need to get down to a size 1 array? Because that's when your base case happens. And that turns into a question of how many times can I chop an array in half? Yeah? So to get down to subarrays of length 1 logarithmically quickly or exponentially quickly, because an exponential function is the inverse of a logarithm. So it's going to be about log base 2 of n, recursive calls, right? And log base 2 of n levels in this recursion tree. In the best case, for sure, and also the average case. So on average, you're going to pick a number that's right about in the middle for your pivot element. Does that kind of make sense? And that's why your space complexity, because at each call you have like some work to do, but at each call you're going to just like remember where you came from. And so you're going to have that many calls all at once, like this one, then this one, then this one, then this one. There's only going to be the height of the recursion tree number of calls on your stack at once. So they each are using constant space, but just them all happening at the same time, waiting on each other. That's what gives us logarithmic space complexity. But yeah, that's what happens there. And again, to get the running time complexity now, kind of think about what happens. At this level, we're looking at n elements. You're swapping things, getting them in the right order. At this level, these recursive calls, you still are adding up to n work to be done on each piece of that array, right? You're swapping n over 2 things, and you're also swapping n over 2 things over there. So it adds up to n work there as well. So n work at this level, n work at this level, n over 4 swaps, but 4 times. Again, O of n work at that level. And so at each level, you're doing n work. How many levels do you have? Log base 2 of them. That's why we get n log of n time complexity. That's kind of the short story. Okay. Are there any questions about that? Your book will explain it in more detail for sure, but that's what I wanted to say for now. Does that make sense for the average case, for the best case? You cut it right in half with a good pivot element. That's how that works. Because you could have a horrible pivot element. What if you chose, for example, a pivot element that ended up going right here? See how that's horrible? Because it's like you've got a size 1 subarray over here, and then you have a size n minus 2 subarray over here to go in quicksort still. The question is, how deep does this tree go now for the recursion? And again, let's say you pick another horrible pivot element that like splits it like that. You have this size 1 to sort, and now this size 1 to call quicksort on. N minus 4 elements or something. Do you see how the height of this tree is going to be n over 2, I guess? The height is going to be O of n. Yeah? And from this like analysis, you're doing n work at each level times the height of your tree, your recursion tree. You're going to do n squared work in the worst case now. All right? But you can avoid that. You can avoid the worst case if you just like always do a random pivot element. Don't like hard code which index you're going to look at, because if say your array was in perfectly reverse order or something, you'd end up with this problem if you always choose the first element as the pivot, something like that. So choose a random element. On average, your random element, which should be about in the middle of the things that you have. Okay? And so that will also turn into O of n space, because you have that many calls on your stack waiting to be completed. That's disgusting. So that's quicksort in a nutshell. I'm not giving you the pseudocode because there's a lot there, but I hope you have the intuition. That's all I really care about, you getting. Okay? Any questions about that before I show you the animation? It's going to be fun. So the animation it's going to go fast because this is a fast algorithm. Maybe I'll slow down the speed just for now. Whee. But I'm going to click quicksort, and you're going to watch it get down to the base case, and then it's done at that point. So you'll watch it start by partitioning the whole array, and then it'll get the thing in the right spot. Let's slow it down as slow as I can get it, maybe. Whee. So it's the partition element is it's chosen 41, I guess. And so it's essentially now it's drawing a line, and it's going to start putting things that are smaller than 41 on the left side of the array and bigger things than 41 on the right side of the array. And so it's like working its way inwards with it's got an I index and a J index, and it's swapping things that are in the wrong spots. And so if I make this slightly faster, you can watch it happen. Come on, you can do it. There we go. This is one round of partitioning. And then by the end of this, the 41 will be in the right spot, just like where they meet, where those indices meet. And then it just needs to quicksort this smaller array and that smaller array. Does that make sense? That's what it's going to do. And it's going to recursively do that until it gets down to size 1 or size 0 subarrays that don't need to have anything done to them anymore. And so it's just like highlighting what it's looking at right now. So you're at like the lowest level of the recursion. And you're just watching it work. But quicksort is probably the fastest one that I'm showing to you. It's got the best constants. It is n log n. It's as good as it can be. A logarithmic space. But yeah, if you pick a bad pivot, you might have a lot of work to do. See, that wasn't perfectly in half. That size of the array was like from here to there or something. It was about in the middle, though. On average, it'll all work out to n log n. But that's quicksort, and now we know. Questions about that? See it? All right, I want to show you a cute little video. I have to pause the recording because I don't want a copyright strike. Unpause, land. So I like that a lot. But yeah, quicksort is a good one to study. It's a good one to have memorized, I would say, for the future. Don't have to deal with it right now. But let's see. Yeah, I think that's what I wanted to say about it. Are we ready for merge sort? The last one I want to show to you. All right. Merge sort is probably conceptually the easiest one. I will show you an example of it. I've written it out already. I'll give that to you. But merge sort is also very cute. It also has a helper function. It can't do it all itself. That function is called merge. I guess you just like copy and paste that into the body, but it's easier this way to think of it. So merge sort is exactly this picture. It's what you would imagine if you were making a sorting algorithm. What it does is it chops the array right in half, and then it recursively sorts each smaller array, and then it has to merge them back because they're going to be like, you can't just like put them right next to each other at that point. I'll show you why. So let's say we've got these elements: 8, 6, 7, 5, 3, 0, 9. That's our jumbled array. It's going to chop it in half as good as it can, right? This is a odd number of elements, so you either got to chop it like this or like this. Let's pretend we chop it like this. Boop. And now we've got two smaller arrays of essentially half the size. As good as we could make half, all right? What you will do is you're going to recursively sort them now. You're going to say, all right, for these indices, that's the smaller array. Go and recursively sort those, and you will get back, you can just like, thanks to recursion, it's a smaller array, you're guaranteed to get back the array 6, 7, 8, yeah? If you go and recursively sort this half, oops, weird, never, okay, sure. If you go and recursively sort this half, you're guaranteed, just imagine that you got back 0, 3, 5, 9. And now, your job is to sort the original elements, right? You can't just like, take this and put it next to this. They're not in the right order anymore, but they're close. They're close enough to being sorted. You want to now merge them. You want to now merge them back. So you call the merge function to bring them back, merge, into a new array. You're going to place them in there. All right. Merge sort it needs an extra array here. You got to make another array of size n if you're merging n things. You cannot do this in place. So merge sort has worse space complexity than quicksort. But here's how it works. You got your I indices and your j indices. I starts here and j starts here because you're trying to fill this from left to right. What's the final sorted thing? Do you see how the thing that needs to go right there in that first index is either this thing or this thing? Guaranteed, right? No other options. So it's like, who wins? 0 or 6? The 0 wins. Boop. And now, so you advance your j index. So now it's 3 versus 6. Who goes in the next index? 3. Then you advance your j again. J's winning. Now it's 5 versus 6. Who wins? The 5. Advance the j. And now it's 6 versus 9. Who wins? The 6. Advance the I finally. 7 versus 9. Who wins? 7. Advance the I. 8 versus 9. 8 wins. Advance the 8. And then you notice that you've exhausted this array, so you just take what's left of the other one. That can be the algorithm. So put the 9 there. And so that was we had to make a brand new array to put all those guys in because we're copying and pasting them, kind of. So we needed some extra space in a brand new array, and you kind of then you copy that back into the original one. You copy that back into the original one, and that's what happens. All right. So you do need that separate array to do the merging. You could not do it in place. Let me show that to you with a size 4 example. And then you can extrapolate from there. Let's say you've got 2 smaller subarrays. Not partitioned. We've divided and conquered this left side. Now it's sorted 1, 5. Now I got 2, 3 here. If you were to play the same game in place without an extra copy of a size 4 array, like you'd be like, all right, 1 versus 2, who goes where? The 1 is in the right spot. Cool. Now it's 2 versus 5. Who's in the right spot? Well, the 2 wins, so I'm going to swap the 2 and the 5. This will never work because now you're like, okay, I've exhausted this array. Then I'll just take everybody over here in order, and I have now sorted it. It goes 1, 2, 5, 3. I'm done. So it doesn't work like that. So I hope that is slightly convincing. You need a brand new array to bring things into. You have to copy them in, then you copy them back. Okay, so that's a bit worse of space complexity. Time complexity is going to be the same as quicksort, though. This is the conceptually easier one, I would say. All right. So does this idea of chopping it in half, recursively sorting it, trusting the recursion, and merging them back make sense? That's the code. And so that's definitely easier conceptually than quicksort. And so I'll show you code for this in just a second. But let's do this. Let's do the complexity. So yeah, it is guaranteed because of the way it's chopping things. It's making sure it's in half. If it's odd, it does its best job. But it's all going to work out. So it's for sure going to be log of n, watch. Log of n recursive calls in your recursion tree because it's going to chop it, right? It's like, okay, chop these in half. Recursively go and merge sort the 2 smaller halves. They're guaranteed to be cut in half because we're for sure chopping it in half. We're not letting that be up to chance. We're chopping it always in half. And then we're just recursively merge sorting this and this, which is going to involve, okay, let's chop this in half. Let's get down to this size array, go and merge sort that. Get down to this size array, go and merge sort that. That's what's happening. And the merge process kind of built it all back up. So then, all right, we got these. Let's chop those in half. Recursively recursively merge sort. Got this one, recursively merge sort. Maybe this is all size 2 or something now. Chop them in half, recursively merge sort, recursively merge sort. The base case of merge sort is the same as the base case of quicksort. You've either got an empty array or a size 1 array, let's say. It's already sorted, yeah? And so, let's say we're in this call. That's going to be the first call that finishes. We will take, all right, we notice that this one's completed. It's sorted, cool. This one's sorted, cool. We come back and we merge them back into this original array. That's of size 2 now, let's say. So that's what's going to keep happening. Like that gets merged back into there. These get merged back into here. In sorted order now. You play the game of you do the loop. Right? You do that loop. And then now you got these 2. These are sorted. And so you're going to go through them all, each index. It's a linear time thing, right? To merge them back into this big array. Merge them back into this big array. And so now, thanks to the recursion, we're back to here. These are now sorted, these guys. You're going to merge them back, playing that same game. Into the original array. Okay, so I hope you see that the merge process is a linear time thing. It's going through all these elements and placing them here. So you're going through all of the elements, linear elements, and linear work. Yeah, and that's what's going on. And so I hope you see that the number of levels. How far do you need to go down until you get a size 1 thing? It's about log base 2 of n times, right? Log base 2 of n levels. So that's how many things are going to be in your recursion. And at each level, how many elements need to be merged? At this level, you're merging n elements, right? Back into the original size n thing. But that's actually true for everyone. At this level, you're merging back into here and into here. So it's n over 2 elements being merged back, n over 2 elements being merged back, constant work per element. So that's, again, n work being done at this level. Does that make sense? N work being done at that level to fill in those two smaller subarrays in their sorted orders. So n work done here, n work done here, essentially. There's n things to merge at each level. It's always the array itself. Just they've been chopped in some way. But they're all still there and accounted for. Okay, so there's log base 2 of n levels, and you're doing essentially, you're looking at n things and doing constant work on each of them, placing them into the right spots at each level. So that gives us n log n. Again, that's n log n time, always. No worst case. That is the worst case. We're chopping in half always. We're making sure. But the space complexity is linear. Space complexity is going to be linear because you need another copy. You need to make a copy of the array that you're merging back into, and then you copy it back into the original one. So that's what happens there. That's why you need that linear space, because each merge requires a temporary array that's going to be the size of the thing you want to merge back into. So this call, like the very first call, needs a temporary array of size n. The next call that's on the stack needs a temporary array of n minus 2, or n over 2, then n over 4, then so like you add them up, it's like n times 2 elements that you need. So it's linear space. All right, that's what's going on. So yeah, that's why it's like that. Quicksort is supposed to be slightly faster than merge sort on average in practice. Slightly better constant out in front of the n log n. Because it's in place, you don't have to copy and move memory around. Slightly faster because of that kind of idea. But asymptotically, at least, it's n log n. So just as good. Just as good in that sense. So yeah, let me show you that. And I've also got a pre-programmed example. Give you actual C++ code. But merge sort, you're going to watch it. I'll have to scroll down because it's going to have its little temporary array right there as well. It'll be written down there. I mean, you already clicked it, you know. But let's click it. And so, all right, it's chopped it in half. It's working on this half, chop it in half again, chop it in half again. So it's getting down to the lowest level of the recursion. Where's the base case? That. That's sorted. Okay, these guys, let's work on those. Let's merge them back into, okay, this array 1 and 47. Cool. Now they're sorted. Now we're working on these two. Again, base cases, but we can merge them back. Are they in the right order? Yes. Copy them back into the original one. So now we got this size 4 array. I guess I have to zoom out so you can see it all. It's bringing them there. That's interesting. I can't go scroll down any further. Is it like that? Do I need to be like this maybe? It's bringing them back. And I hope you see that it just made a size 4 array that was sorted. And that's what happened. Darn. Yeah, it's just the way this website was written. But now it's all right. It's got those guys. It's gonna merge them back. It's like, okay, bring the ones that are in the right order, and then it's gonna copy. This is your helper space. Your copy. You copy it back into the original. So that's what's going on with merge sort. Speed it. You can watch them merge back. So you got like this part sorted, that part sorted. Now it's working on the right half of the array. So this guy's sorted and waiting to be merged. Sorted and waiting to be merged. Now it's finally merging them back, copying them into the original array. Does that make enough sense? That's fun to think about. But I hope you can kind of get a feel for what the recursion is doing too that way. Like you see it working its way down. It's going to make this kind of traversal. It's going to get to there first. All right. Yeah, so let me show you some code for merge sort, and that'll be it. I want to copy F24 code from class 41, 23. So here is some code that does all this, and here is me calling it. So I've made my vector. I'm saying merge sort vector v from these indices. All right, because you're always going to call merge sort on which size array do you want to merge sort right now. I want the whole thing sorted. So from index 0 all the way to size -1, please. And then it should be done. It will sort them back, and we'll see it in sorted order. So this is just a very complicated program that prints those in sorted order. And so let's look at merge sort. So merge sort calls off to merge, but let's just look at it first. So merge sort is either like, it's recursive, right? It's divide and conquer, which implies it's recursive. We're sorting this vector v from between these indices, start to end inclusive. So the base case, we need to notice if we're in the base case or the recursive case. If we're in the base case, that means the array that we want to sort is size 1 or even less, or 0. So it's already sorted. We can just return if that's true. Yeah, that's what that means. So like if the indices, like the distance between them is 0 or even less, then return. Then we're done. And yeah, otherwise, let's chop it in half. Where's the half? Halfway point. Take the average of the indices. There's my halfway point. And so I'm going to recursively sort those small arrays between start and mid plus 1 and end, right? Because we're sorting from start to end. So the left half is from start to mid. The right half is from mid plus 1 to end, non-overlapping, right? And then the goal is to merge them back. So I've made a merge function that takes the array, or sorry, the vector, and the start index, the midpoint index that's like section them off, and the end, and it will use those to know like, all right, I know that I've got something sorted from start to mid. I know that I have something sorted from mid plus 1 to end. Let's merge them back. All right, so does merge sort make sense? Do you see how the recursive case is working? Chop it in half, sorting the left half, sorting the right half recursively, then calling merge in a way that it can understand where the left and right halves are. Because yeah, you see it working. And then merge, that's the one, it's not recursive merge, but it's got a lot of loops. It does weird things. So there are some special cases. So the idea is we've been given start, mid, and end, and we know, due to the way that's been called, that we've got a sorted array between start and mid. Those indices have been sorted. And then mid plus 1 to end, that's another separate subarray that's been sorted. And we want to merge them back into those indices again. So I've got my I and I've got my j, just like I drew. I've got my I and I've got my j on the left sides of each of those sorted arrays. So like the first index is start for the left one, it's mid plus 1 for the right one. And like those are the first elements that's going to go in the final array. We're going to make a temporary array though of the right size, that many things, to have them placed where they need to go. All right, and so then this is the main loop. This is the main loop where we still have things in this left array and things in this right array. We need to decide between them. Which one goes where? So while I still have stuff, well, I is not yet at the end of that one, and j is not at the end of the right one, then go figure out which of the two wins, which of the two is smaller, and that's where it's going to go. You're going to place that thing in the temporary array. I guess I could have called pushback to make it slightly easier, but like this is more memory efficient. So yeah, like that's the next index, next open index in my temporary array. Place it was thing at I that won out, so I plus plus. Otherwise, it was thing at j that won out. That goes in the next index of my temporary array, j plus plus. Then I'm going to fill in the next index after that. So does that make sense for the general case of merging? It's like find the smaller one, place it in the open slot in the temporary array. We're good to go. And eventually this will become false. This loop will stop when either like I've got them all in the right spot or I've exhausted one of the two. I've exhausted one of the two arrays. I just want to take the rest of the other one. All right. Exhausted one of the two. So once the loop is done, we've run out of one of the small, I guess it's always going to be one of the two. We've run out of one of the smaller subarrays. So like we've gone through all of, so this happened for this one, right? We've gone through all of the I array, just like we only had the 9 left. Go through the rest of the other array though, because there could have been like a 10 over here. So like go through everybody else and bring them all in now. Like that's one of the details that you have to remember. Oops, I guess that works. So like, all right, who has been exhausted? All right, if the left half has been exhausted, then give me all the rest of the j's until the end of the right half. Keep going. Otherwise, the j's have been exhausted. The right half has been exhausted. The left array still has stuff. Go through the i's until the end, and then at that point, you've taken everybody. Everybody's in that temp array. Then we just want to copy that entire temp array. We've called it temp, right? Which has indices 0 through something weird, and bringing them back into start through end now, which are some other indices. So there's some math that needs to take place there. It's like, all right, this is the index, like from start to end is where I'm filling in the original array, go through the temporary array at like index idx, and I'll just advance that each time, just like to keep the math easy on myself. So that's me copying it back into the original vector. That's the merge process. Does that make enough sense, all the special cases? It's a little weird, but again, you'll read about it, you'll see more animations in your book, and Yeah, it's really fun to think about. It's like these are like the standard things you want to learn how to analyze, and we've been talking about them, so that's good, and you've been understanding, so that is wonderful. Yeah, it is recursive. Recursion is very helpful for sorting. It gives us our n log n time. Beautiful. And so yeah, I saw it run already, and that I think is all that I wanted to say about merge sort. Are there any questions about it? So hands off the problem to the merge helper function. We know that there's a lot going on in that one now. All right. Yeah, I think that's where I wanted to stop for the day. Let's see here. I will prove to you eventually that n log n is as good as you can do. I'll prove that to you next time, I guess. There's a way to get it down to linear time sorting, but that doesn't work for arbitrary things. Only certain kinds of like whole number, like ints, you can sort in linear time technically using a cool algorithm, but like strings you could. Arbitrary things that involve like the less than operation. N log n is as good as it can be, which is exciting. You know the best general purpose sorting algorithm now. It is quicksort, more or less. There are slight improvements that people have made, but that's really, really, really good. Asymptotically, you cannot do better than n log n. So you know quicksort, you know merge sort now. It's great. Questions? Yeah.
So like in general, in like most applications, just quicksort for sorting algorithms.
Yeah, it depends. There's sometimes when you want to do merge sort rather than quicksort, there's a difference between them that I haven't gotten into that you'll study more in like a 4-year college's algorithms class. Quicksort is called or merge sort is called a stable sort. Quicksort is not a stable sort. And what that means is, say you had the numbers 1, 2, 2, 3 in your array, and they were jumbled though. Like it went, I don't know, 3, 1, 2, oh gosh. I need to get them out of order. 3, 2, 1, 2. A stable sort will make sure that in the final output, this 2, the first 2, comes before the second 2. So merge sort will guarantee that. Quicksort does not give you that guarantee. It will maybe put this 2 before the other 2. There are some times where that's important. Usually numbers are not important, but there are some things that you might want to sort where you want stability. You want the first thing that was a duplicate to remain first in the final sorted output. That is beyond the scope of this class, but that's one reason you want not quicksort. Yeah.
C++, the C standard like algorithm uses quicksort.
I believe so. It uses some version of it. Let's go look at the documentation in the algorithm. There's also a stable sort function, I believe, for this exact reason, because you maybe want that. Algorithm. So let's look at both. If it wants to load, though. Good timing for the website to be down. Oh, man. Is my internet just down? Look at this. No, it's just that website. That's why we have archive.org. Ta-da! That's horrible. All right, sure. Wow, the website is down right now. Everybody's trying to get algorithm analysis questions answered. All right, we've got... Where are our sorting things? There is a sort and a stable sort. They're not the same. So click on both. Dun, dun, dun. Elements are not guaranteed to keep their original relative order. Bless you. It is going to be, on average, n log n, which is implying quicksort to my brain, right? Because worst case is n log n for merge sort, so it can't be that if it's saying average right there. So it's most likely a quicksort or something similar to quicksort. It's definitely not stable, not guaranteed to be a stable sort. Different libraries could, like you could make your own C++ standard library if you wanted to, like implement all these things. You could make it be merge sort, but this is what all the library people have guaranteed, like on average this, which implies that you could use quicksort here. Like one of the libraries probably use quicksort here. There is also a stable sort function, which is cute. That one, if enough extra memory is available, n log n, which is implying that you need some extra memory, and then it's always n log n, so that's implying quicksort, or sorry, that's implying merge sort or something similar to it. So that's, yeah. We can go into the implementation. Like you can go look on GitHub, like the implementation of the G++ standard library. I don't know very quickly how to find that for you though, but we can look at it together. That would be a great thing to find, maybe after class. But yeah, does that answer our questions? Yeah, other ones. These are good to know. This one day you will care more about this. It will be an algorithms class at a 4-year college though. Fun stuff. You've seen a piece of it though. Yeah, I think that's all that I wanted. So yeah, we'll get to that next time, those other things, and that's where I want to stop for the day.